Hello everyone, this is VR Physics. Today we're going to cover thermal physics. It's topic 3 on the physics IVDP course. It's a very simple topic with only two divisions known as thermal concepts as well as modeling of gas. So before we go any further, we have to establish a few units. First of all, Celsius degrees. We use Celsius degrees in our normal life. Then there's the Kelvin. In case you add 273 to a Celsius value, you'll get the Kelvin value. Thus, Celsius is maximum negative 273, which is absolute zero, at which point nothing moves. There's another additional unit, which is known as Fahrenheit. Fahrenheit is not used so much in the scientific process as that it can be converted into Celsius, which can then be simply added 273 to get a Kelvin. Now, moving on from that, the first understanding must be that while there's a change in an object's temperature, with the help of a specific heat capacity, one can calculate the energy produced. Energy is also produced when something goes from a liquid state to a gas state, or from a liquid state to a solid state, and vice versa. These are known as the three phases of matter. There are higher points beyond gas and lower than solid. However, those will not be covered in this topic, so don't worry. So this basic equation for the energy produced when something is either cooled down or heated up is Q equals to mc change in T. Q is obviously energy, and M is equal to the mass of the object that's being cooled or heated up. C is the specific heat capacity of that particular object. Specific heat capacity does not change based on object to object, but rather from material to material. For example, water and honey would have different specific heat capacities. Then the change in T. This can be denoted in either Celsius or Kelvin, because when subtracted, you get the same answer. So this is the equation for the energy produced while something is being cooled down or heated up. Now we shall go on to when an object changes phases. So going from solid to liquid, liquid to gas, gas to liquid, and liquid to solid. So that is, in that case, Q will equal to M times L. Now, M obviously is the mass of the object that's being converted, but the L, it's the latent heat, latent heat. So there will be a subscript depending on which phase it's changing into. For example, vaporization or condensation, so on and so forth. So the subscript will change, and thus there will be different values for the latent capacity. Now this is basically the first part covered. Now let's move on to the second part, which is modeling a gas. So for modeling a gas, the first thing we need to understand is the concept of ideal gases. Ideal gases are gases which only have kinetic energy. Well, it'd be more important to say first before going on to that. Ideal gases are models created by scientists so as to easily understand what's going on inside of a gas. Ideal gases only have kinetic energy. They also only have they have the same average speed. However, the individual speeds of the different mass particles will vary. The mass of any particle in an ideal gas will be the same. The collisions are short. So now that the ideal gases have been established, we can go on to pressure. Pressure, everyone knows, pressure is the force over area. This can be converted to understand to get the force or the area, and with simple algebra. Then we get the number of moles. Okay, so moles, I've already covered this in our previous physics video, is the amount of stuff in a certain amount of material. For example, 12 grams of carbon 12 will have 1 mole. That's the basic explanation for what a mole is. For mole, we have an equation n equals n over a. n over a is Avogadro's constant. Avogadro's constant is what 1 mole represents, which is 6.02 times 10 times 10 to exactly. Thank you, backseat person. N is the number of stuff that's actually in the place, and so we get the mole of any particular area. Now we can calculate equation for to connect pressure and temperature. Okay, P equals to the pressure, V equals to the volume of the space containing the gas, N equals to the number of moles, which can be found out by the previous equation. Then R equals to another constant known as
8.31.
Yes, it is 8.31, but it is also known as the gas constant. This is also an equation that's shared with chemistry, and you'll see it appearing in our chemistry videos as well. Similar things, as I've stated. Then the T is the temperature. We've already talked about how there are different measurements. The T must be in Kelvin, and it is very important that it must be in Kelvin because the Kelvin is the scientific measurement unit. So keep T in Kelvin. Don't put it in Celsius or Fahrenheit. Keep it in Kelvin. It's very important. That's why I've mentioned it quite a few times. Now let's get to the definition of what a temperature is actually. It is the average kinetic energy. It is a measure of the average kinetic energy of any object. And for a more direct equation, we have. Now this is the direct relationship between the average kinetic energy and the temperature. Here we see 3 to the power of 3 over 2 times R over NA, both of which are constant. Thus we are able to deduce this constant over here. And then the T is once more in Kelvin. It is very important that you do the calculations in Kelvin. Celsius and you'll get everything wrong. Fahrenheit, why are you using Fahrenheit? Seriously, I told you not to use Fahrenheit.
Hi, thanks for watching this video from our video revision series. To watch other videos from this subject, click the playlist on the right. And to see the bloopers of this video, click the video to the left. Make sure to leave a comment with any topics, suggestions you may have, and subscribe to see when it comes out.